Hello, this is Mrs. Taylor, and I'm going to demonstrate for you how to expand a binomial raised to an exponent using the binomial theorem. So the directions say expand completely using the binomial theorem, and our problem here is 1 plus 2y all raised to the fourth power. And using the binomial theorem is a shortcut, because if I were to expand this not using the theorem, I would have to write it out as 1 plus 2y times 1 plus 2y times 1 plus 2y times 1 plus 2y, and then multiply all that out. It'd be very time consuming. So the binomial theorem is a shortcut that takes me directly to the resulting polynomial I would get from multiplying 1 plus 2y times itself 4 times. So in order to use the binomial theorem, I need to know the formula for finding the coefficients for each of my terms in my polynomial. And that formula is n factorial all over k factorial times n minus k factorial. And n represents your exponent. So in this case, n would equal 4, because that's the exponent I'm raising the binomial to. And k represents your term number of your polynomial. So k always starts as 0. And then for each term for your polynomial, it will go up by 1. So you'll have the 0 term, first term, second term, third term, and so forth. All right, so the way I get my coefficients is I use this formula. So all I'm going to do is I'm going to go down the line and fill in this formula for each coefficient for my polynomial. And so to start with, n equals 4. 4 factorial is all that's on top of this formula. So that means every single coefficient will start with 4 factorial. And then k factorial for my very first term will be 0, because it's the initial term. And then 4 minus 0 would be 4, so that would replace the n minus k. So it would look like this once I fill everything in. I would have 4 factorial, because that's the exponent, 0 factorial, because I'm working on the first term, and the term number of the first term is 0, and then 4 minus 0 would be 4. That's where this 4 factorial came from. So then I'm going to throw in a plus sign, give some space, because I know I'm going to have some variables and things here once I move on to the next step. And then I'm going to repeat the process. N factorial does not change. So again, the next coefficient will have 4 factorial on the top. However, on the bottom, it does change, because I've moved to the next term. So that means my k value is now 1. And 4 minus 1 is 3. So my next coefficient would be 4 factorial over 1 factorial, 3 factorial. And then I'm going to throw in a plus sign. And continue that process. So the next term, the coefficient, again will have 4 factorial on top, because that doesn't change, but now it's the next term. So we're going to go up to 2. 4 minus 2 is 2. So I have 4 factorial all over 2 factorial times 2 factorial. Put a plus sign, leave some space, and repeat. 4 factorial stays the same. We're in the next term, so that goes up to 3, and the 4 minus 3 is 1. Put in my plus sign. Oops. And then once again, 4 factorial is always on top. And then this is the next term, so that will go up to 4. 4 minus 4 is 0. So now I know I've reached the end, because I started with 0 here on the left as my term number, and now I have 0 on the right, which means I've reached the number of terms that I need in order to have my complete polynomial. When you subtract n and k and get 0, you know you've finished. Okay, so from there, I pretty much do the same thing I did with Pascal's. to find out what my variables and the other parts of these terms are, all I have to do is use my first term of my binomial, raise it to the exponent that's in your original problem, and then the second term of your binomial gets raised to the 0 power. It's the same every single time. First term gets raised to the exponent, second term gets raised to 0 power. So when I enter that into this first term of my polynomial, it would look like this. I would have my first term 1 raised to the 4th power, and the second term to the 0 power. So the pattern for expanding your binomials is that the first term's exponent goes down by 1 as you move left to right, and the second term's exponent goes up by 1 as you move left to right. So your 1 to the 4th would then become 1 to the 3rd for the second term, 1 squared, 1 to the first, and then 1 to the 0 power. And then the 2y would increase. So for the second term, it would become 2y to the first, then 2y squared, then 2y cubed, then 2y to the fourth. So typing all that out would look like this. For my second term, I would have 1 cubed and then 2y all to the first. The next term, the cube will become squared, and then the first would become 2, and then so on. So that's the pattern for the two terms of the binomial when you create your expanded polynomial. Right, so the next thing I have to do is simplify. And I could simplify several ways. I can remember the patterns, first of all. For all of these expansion binomial problems, your first coefficient always, whether you're looking at Pascal's or you're simplifying the factorials, always reduces to 1. And then the second term's coefficient here always reduces to whatever the exponent is. So I know that this first fraction with factorials will reduce to 1, and this second will reduce to 4. I also know that it's symmetric because of Pascal's triangle. So if it's 1 as the first term, it's going to be 1 as the last term. If it's 4 as the second term, it'll be 4 as the fourth term because the coefficients are symmetric. Now, if I happen to forget that, I could also look at Pascal's triangle to remind myself. Look at the row that corresponds with the exponent of 4, which would be the 5th row on the triangle, and I would see the same thing. But let's say we didn't have access to that and we still needed to simplify. I just want to show you how to enter that in your calculator just in case that's the method you choose. So let's say we were entering our first coefficient into the calculator. 4 factorials on top of the fraction. It doesn't have anything up there, so I don't really need parentheses. I just need to enter 4 factorial. And if you're using a graphing calculator to get to that, you go to Math, over to the probability menu, and then it's option number 4. And then divided by will give me the fraction bar. Now I have multiple things on the bottom of the fraction, so that means I need to be using my parentheses. And the 0 factorial, and 4 factorial. Close the parentheses, press enter, and it gives you the reduced value, which is 1. And then I need to go ahead and evaluate the exponents. Well, 1 to the 4th would just be 1. And then 2y to the 0 power, well, anything raised to 0 power is going to equal 1. So my first term of my polynomial actually reduces to just 1 times 1 times 1. Which I hope everyone out there knows when you multiply that out, it's just going to be 1. So my first term reduces to just 1. And then I continue to simplify. So for my next term, which would be right here, I have 4 factorial over 1 factorial times 3 factorial. Well, we've already discussed that we know this is going to reduce to 4. And then I have 1 cubed, which 1 to any power is just going to be 1. And then I have 2y to the first power. Well, raising something to the first power does not change it, so that would just be 2y. And then 4 times 1 is 4. 4 times 2 is 8. So this would become 8y. And then you continue to simplify in this way. So my next term, if I'm looking at Pascals, if I'm entering it in my triangle, or excuse me, if I'm entering it in my calculator, either way, this 4 over 2 factorial, 4 factorial over 2 factorial times 2 factorial would reduce 6. And then 1 squared, again, is just 1. And then 2y squared, well, I have to square the 2 and the y. So that would become 4y, and then that y would also be squared. So then I multiply these coefficients, 6 times 1 times 4, and I get 24. So the resulting simplified term would be 24y squared. And once I continue simplifying the rest, the result would be 1 plus 8y plus 24y squared plus 32y cubed plus 16y to the 4th. So that would be my resulting polynomial after expanding this binomial. And that's how you use the binomial theorem.